Okay. Now, share screen. There it is. Okay, excellent. Assuming this is visible. So I have absolutely no idea where this talk came from. That is, I have no idea what led me to a paper that was published in the American Mathematical Monthly in 1914. And the title of Kempner's paper is A Curious Convergent Series. Only Dick might possibly remember, but it's impossible to remember, that I have previously spoken on some work of Kempner, because at the beginning of the 20th century, there was a series of papers having to do with Waring's problem for cubes. And the idea was to prove that every non-negative integer is a sum of 9 non-negative cubes. And someone would publish a proof, and then the next person would say, oh, it's a nice proof, but there's a mistake, and here I correct it. And then the next person would say, well, that was nice, but there was a mistake in that also, and here I corrected. And somewhere in this chain, there was a guy named Kempner at the University of Illinois who corrected the previous proof, but his proof also had a little mistake, but it was the penultimate mistake. And then the last paper in the series actually filled everything up. So what Kempner called a curious convergent series is the following. So I'm just going to quote from his paper. It is well known that the series 1 plus a half plus a third, that is the harmonic series, diverges. The object of this note is to prove that if the denominators, that means 1, 2, 3, 4, do not include all natural numbers, but only those which do not contain any figure 9, that means any digit 9, then the series converges. So from the set of all integers, if when you write them down in the standard decimal notation, just exclude all the ones that have a 9 in the decimal representation. And miraculously, as Kempner proved, that infinite series converges. And he continues, the method of proof holds unchanged if instead of 9, any other figure 1, 2 up to 8 is excluded, but not for the figure 0. That statement I don't understand, because it is true the method of proof holds unchanged for every digit except 0, but if you add one sentence, the right sentence, it also holds for the figure 0. So there's nothing significant about that. And a few years later, oh, sorry.
No paper is complete without a mistake.
Oh, well, this wasn't a mistake. What he's saying is it works, the same proof holds. Well, actually, he says the method of proof holds, but not for 0. So for 0 is a little bit of a special case, because if you have a k digit number, the first digit is not a 0. Otherwise, you don't have k digits. So there's a little bit of refinement in the proof that you need. And this theorem has been, the same proof works in the following slightly more general case. If you take an integer g, at least 2, and you write an integer n in its g-adic representation. So, summation cig to the I, where the digits are integers between 0 and g minus 1. So every number has a unique g-adic representation. And if you look at, and if you pick a digit, the digits are these first g non-negative integers. If you look at all the integers whose g-adic representation never contains the digit c, then this harmonic series converges. And it's in this form that you'll find it, for example, in Hardy and Wright. It's a very nice result. Now, so the g-adic representation is a sort of a special case of a more general way to write the integers. So this is a capital script G, math calligraphy G. So a g-adic sequence is a strictly increasing sequence of positive integers, starting with 1, such that each term divides the next. Gi divides gi plus 1. So that means that the quotient is an integer, And because the sequence is strictly increasing, each of these quotients is at least 2. And so, you know, G1 is G0, D0, and so forth. In general, GK plus 1 is the product of these quotients, D0 up to D sub K, because G0 is 1. And every positive integer has a unique representation in this G-adic series. We call it the G-adic representation, where the digits depend on I. So the ith digit is an integer between 0 and D sub I minus 1. Again, a few years ago, I spoke about this kind of representation in the seminar. It came up in some papers of De Bruijn. And at one point, I remember I wrote a kind of expository article that was published in the monthly on De Bruijn's theorems. So, so what I want to do is try to extend Kempner's theorem from decimal representations or G-adic representations to this more general script G-adic representation. And that's a natural question to ask. If you take this more general representation and if you exclude a certain digit or even a set of digits and just look at the resulting numbers and form the harmonic series, does the harmonic series converge? And the answer is not the exact analog of Kempner's theorem. The answer is sometimes this new harmonic series converges, but other times it will still diverge. And so there are 2 cases. So that is like the new thing, I guess. So we need a certain technical lemma, which is the following. So suppose we have this G-adic sequence of integers. So they're positive, the smallest is 1, and they're strictly increasing. So these quotients are integers at least 2. And what I'm going to do is, what Kempner did was look at all the integers that don't have a 9 in their decimal representation. So, but I'm going to weaken that a little bit. That means I'm going to throw out more integers perhaps, or less integers. So you could, for example, say, suppose we look at all integers and we put no, like even in Kempner's case, we put no restriction on like the odd digits, like in the ones and the hundredths and the 10,000s, like, but we only look at the even digits in the number. That is the 2nd, the 4th, the 6th, and only look at the numbers where none of the even digits is a 9. So now we are throwing out fewer numbers. So the infinite series in some sense is bigger, and does it converge or diverge? So I want to, I could just say, okay, look at all the digits, but it's a stronger result or more interesting to say, suppose we take a set I of non-negative integers. And so I'm only going to look at, so when you write a number in its G-adic representation, so the number C sub I, this is the ith decimal digit. And I'm only going to put a restriction on the ith decimal digits for certain i's, the i's that belong to the set capital I. And for every I in this set, I'm going to choose a non-empty proper subset of the possible values of the ith digit. That is, the ith digit is an integer between 0 and D sub I minus 1. And I'm going to take a non-empty proper subset of the digits. And so for every k, if I look at the interval from G sub k to G sub k plus 1 minus 1. So this means exactly all the numbers that have exactly k plus 1 digits in their representations. And in this interval, I want to consider all the numbers that satisfy the sort of the following missing digits condition, that we throw out any number whose ith digit is in this set U sub I. So we're only looking at numbers n equals summation ci gi, where if I is not in the set I, there's no restriction on the ith digit. But if I is in this set of special set I, we don't consider any number where an element of ui is one of the decimal digits. So we're putting restrictions on a certain subset of the digits. And so that's the set A sub k. It's everything in this interval that satisfies this missing digits condition. And the set A sub k satisfies this inequality that, of course, it's empty if k is an I and the set of digits you're excluding are 1 to d sub k minus 1. Now, this means the only digit you can possibly have is 0, but in this interval, the coefficient, the digit for g sub k is positive. So there would be nothing in the set. But if k is not an I, or if k is an I, but it's not this, then the cardinality of the set A sub k, it's basically this. So A sub k is at most this, and 2A sub k is greater than or equal to that. So that's just the counting argument. You think of your the number in this set. It has k plus 1 digits, and there are restrictions on the digits that are an I and not on the digits that are not an I. So if you have an I which is unrestricted, you have d sub I choices of digits. If you have the ith place digit restricted, there are this many choices for the digit. So this is where this estimate comes from. And just because of the number 0, which Kempner tried to avoid, instead of this being an equality, we have this rather tight inequality. So now we can prove a theorem, well, almost a theorem. If you have a set of integers, positive integers, A of n is the number of elements in the set up to n, and what's called the upper asymptotic density is the lim sup of A of n over n. If this limit exists, of course, then we say that the set A has a density, and A of n over n is the density, and the set has density 0 if the density is 0. That's quick. Okay. And there's the following theorem, which I just write it as a lemma, and it is sort of well known, I guess, if anyone needs to think about it, but it's, I mean, I hadn't known this actually, but so I gave a little proof, but it's certainly known. If you have a set of positive integers, if the sum of the reciprocals converges, then the set has density 0. So, for example, if you look at how Hardy and Wright treat Kempner's theorem, they actually give it as 2 theorems. They say if you look at the set of positive integers that are missing a digit, then that set has density 0. That's theorem 1. And theorem 2 is that same set has the property that the associated harmonic series, the sum of the reciprocals of the elements in the set, converges. So the lemma says that you really just need to prove the second theorem, and then density 0 is a consequence of that. But if you're teaching, principles of mathematical analysis at the level of Baby Rudin, it's not a bad homework problem. So here's the theorem. Let's see. So this is a g-adic sequence. So strictly increasing sequence of positive integers.
This private way checking will have a $35 monthly service fee, which can be waived if you maintain a balance of 150.
So we have the strictly increasing sequence of positive integers, starting with 1. These are the quotients, and there are 2 cases. One is that the partial quotients are uniformly bounded. The other case is they're not. If you take, a decimal representation, then d is equal to 10. The gi is 10 to the I, and this ratio is always equal to 10. So if you have a g-adic sequence with bounded quotients, and this is the standard representation of an integer with respect to that sequence, We take a set I of non-negative integers, and for each I, a set of the digits with respect to that I, and that A be the set of positive integers where the ith digit is not in this excluded set. Okay? So this is our missing digits condition. Okay, now, so the set I is a set of non-negative integers if it's at least this big. So, I mean, if I were everything, I of k would be equal to k. But I can actually be a very sparse subset. You're looking, instead of looking at all of the digits, you're putting restrictions on only log k digits up to k times this constant. So d is this upper bound for all the partial quotients. And if I of k is at least 1 plus delta times log k over log d over d minus 1, for some delta greater than 0, then this set of integers with missing digits has density 0, and the harmonic series converges. So you can put restrictions on a very, very, very sparse set of digits, and you still have convergence of this series. On the other hand, with the same hypothesis, we have a geodic sequence with bounded quotients bounded by n. And we have a set of places of, a set of digits, basically. And for each of these digits in this special set, we're going to exclude certain digits. The ones in this set you survive. So those digits will be missing. And if I of k is no bigger than log k over log 1 minus delta log k over log d, then the harmonic series diverges. So if you're excluding only 1 minus delta log k digits, you're not excluding enough. What was our previous theorem? If you're excluding 1 plus delta log k, then you are excluding enough. Of course, the denominators are different. This is d over d minus 1. And this is d. Now, there is one time when d over d minus 1 equals d, namely when d is equal to 2. So we have the following corollary. So now we're just looking, we're actually going back basically to Kempner's case. We're looking at binary representations. So the GIs are just 2 to the I. If you have a set of non-negative integers and you let v sub I be a binary sequence, a sequence of zeros and ones. So if A is the set of integers where, if n is in this binary, this dyadic interval from 2 to the k to 2 to the k plus 1, and if this is its binary representation, so you look at all the integers where for the i's in this special index set, the value of those digits is prescribed. Ci is equal to vi for all I in the set capital I. If I of k is greater than or equal to 1 plus delta log k to the base 2, the harmonic series converges. So if you're throwing out at least, or if you're restricting at least this many digits, the series converges. If you're throwing out less than 1 minus delta log k to the base 2 digits, then the series diverges. Okay. And the proof is just, you look at the previous theorems and apply it in the case when GI is 2 to the I, when you're just looking at dyadic or binary representations. But this is pretty sharp, right? I mean, there's not a lot of space between 1 plus delta log k and 1 minus delta log k. And I don't know what happens in that intermediate case. So it's just an open problem. I mean, it's a week old, so let's not get too carried away here. It's not like, the twin prime conjecture, right? This is like a week-old open problem. So you're looking at binary representations, and you're specifying, you're fixing roughly log k digits. You look at all the integers which satisfy that digit condition, and do the series converge or diverge?
This reminds me of my semi-joint paper with Peter Lax.
Should I ask what's in the paper or what semi-joint means?
Peter Lax wrote a paper called The Differentiability of Paulia's Function. And he had exactly this phenomenon, that there were some infinitesimal gaps where he couldn't decide whether the function was differentiable or not. And I found out how to fill in those gaps.
Excellent. So you need to retool and fill in this gap. Let's see, what else? Okay. So in those two theorems and the corollary, they dealt with the case when I have this g-adic system, but with bounded quotients. And one of the consequences is that if you have a harmonic series with these missing g-adic digits defined as I did, the harmonic series don't always converge. That's what we saw. But if you have I of k, this is the number of missing digits up to k, if it's least log k to the 1 plus delta, and the harmonic series diverges, then you must have unbounded quotients. If you satisfy this kind of inequality with bounded quotients, you would have convergence. So if the series diverges, you have to look at unbounded quotients. That is, lim sup di is infinite. And so I want to prove something about unbounded quotients. And I require two elementary facts. One is this inequality. No. It's true. If x is between 0 and 1, these are positive numbers, but it's bounded below by this. And this is really an important inequality. For example, you need it to write down the order product for the primes, right? You have to know if you take product 1 minus 1 over p to the sigma, that infinite product converges. And that comes from this inequality. So we have a theorem that says the following. We have a g-adic sequence, but this time with unbounded quotients. So these d sub i's, they're not necessarily going to infinity, but they're unbounded. The lim sup is infinite. We have a set of non-negative index, set I of non-negative integers, and for every I, a certain set of digits for the ith digit in the g-adic representation of a number. And A, as usual, is the set of integers that satisfy the missing digits condition. So an AK is just the elements of the set A between GK and GK plus 1. Suppose this series converges. The summation UI over DI converges. So UI doesn't have to be 1. It can be bigger than 1, but can be much bigger than 1, in fact. But this series has to converge. And if that's the case, then the harmonic series diverges. And I haven't proven anything, but that may just give, this really has almost a one-line proof. But first an example. So if you let GI be 2 to the I plus 1 over 2, this is just a pretty example. The quotients are 2 to the I. 2 to the I goes to infinity. So this sequence of integers, each of which divides the next number in the sequence, has unbounded partial quotients. And if you just take the missing digit set consisting of, where you just basically don't allow a 0 in any of the ith places, that will have a divergent series. Even if you take a very big set, if you take like a fraction of 1 minus delta, I mean, almost all, you're taking almost all you're excluding almost all of the digits. Yeah, you have, of course, that's to be expected. It's because you're throwing, well, actually, you're excluding more and more numbers, so you're summing over a smaller set. So this also satisfies that theorem. And so we had these two, this inequality, which is a general inequality, and this was a condition of the, in the statement of the theorem. But this is exactly what it means for this infinite product to converge. Remember, an infinite product converges if the partial products converge to something different from 0. So each of these is a positive number, but less than 1. So as you take the partial products, that's a strictly decreasing sequence of real numbers. But because of this condition and this, let me put these two together, the infinite product converges. So that means that this is, every one of the partial products is bounded away from 0. And using the estimate I had earlier for the size of the set A sub k, if I'm taking the series, so the A is the series of integers where I've thrown away all of the numbers that have digits that I don't like. So this is just the set of numbers that satisfy the missing digits condition. So this is just the same as partitioning all the numbers into these intervals from gk to gk plus 1. And I only have to look at the intervals that aren't empty. And each of those intervals, I have summation 1 over a and ak. And the interval ak was between gk and gk plus 1. So 1 over a is greater than or equal to 1 over this. And cardinality of a, that's just the number of elements in this set. And the cardinality of a by the inequality, this guy, is greater than or equal to half of this. And there's some cancellation, and you get a nice expression of this form. And this infinite product converges. That means every one of these numbers is greater than delta. And so I'm adding delta infinitely often, and that goes to infinity. So the harmonic series diverges. I mean, that's all there is to the proof.
That's a nice argument.
Okay, so that really finishes what I wanted to talk about, but I want to point out a couple of more recent developments. Of course, what does more recent mean? So Kempner proved his theorem in 1914. So more recently, in 1916, wasn't that long ago, Irwin wrote another paper in the monthly with exactly the same title. I have to say, over the last 100 years, there have been a half a dozen papers in the monthly exactly with this title, A Curious Convergent Series. So people like this title so much that they just continue to use it. And what Irwin proved is the following here. So I'm just quoting from his paper, except I forgot to put the right symbol there. All right. So this is Irwin's result. If we strike out from the harmonic series, right, the summation 1 over n, those terms whose denominators contain, so see what Kempner did was throw out every number that contains the number 9 at least once. Irwin is saying, okay, let's allow numbers that have the number 9 once or 0, but we'll throw out the numbers that have 2 or more 9s. Or maybe we can be more restrictive. Let's only throw out the numbers that have 3 or more 9s. Or maybe only the numbers that have 4 or more 9s. So pick your favorite number A, like 100,000. And let's just look at the integers, which when you write them to base 10, have no more than 100,000 9s. They can have 100,000 9s, or they can have 75 9s. But if they have 100,000 plus 1 9s, we discard them, okay? Just look at those numbers. And then you say, well, what about the number 8? So let's look at the numbers that have no more than 100,000 9s, and maybe no more than 10 billion 8s, and no more than 75 7s. So what Kempner is saying is, So for every digit from 0 to 9, he doesn't worry about zeros being special. Let's just have some J numbers. If you check, by the way, J is the 10th letter of the alphabet. I had to like do that on my fingers, but J is the 10th letter of the alphabet. And if you just look at all the integers that have no more than A9s or B8s or CJs or C7s or D6s and so forth, no more than J0s, throw all those out. So as much, you're discarding fewer numbers. The series so obtained will converge. Okay? And so you have to realize that even 100 years ago, people were smart. And Irwin's proof is that it's just this beautiful combinatorial counting argument. It's lovely. More recently, and this was really going against the grain, these two guys, Lubeck and Ponomarenko, published a paper in the Monthly, but they did not call it a curious convergence series. They used a much less original, but more explicit subsums of the harmonic series. And they prove an interesting theorem, where they use a little bit of probability theory. I mean, very little. There's something called Churnoff's inequality, which for sums of independent random variables is stronger than something like Chebyshev. So the Lubeck-Ponomarenko theorem says the following. Take a number lambda between 0 and 1. And a to the lambda is going to be the set of positive integers n. So just think of the number 9. And so remember, we started by looking at integers whose decimal representation contains no 9. So these guys are saying, the previous argument had to do with, well, maybe it contains a 9, but no more than 100,000 9s. So what these guys are saying is the following. Look at all the numbers that, if you just look at the ones with k digits. So a number with k digits is a number exactly in this interval, right? Because in this interval, the leading digit, 10 to the k minus 1 times something, has to be positive. So a number in this interval, so the numbers in this interval are exactly the numbers with k decimal digits. And they want to look at the numbers where in this interval, you have no more than lambda times k 9s. So like if lambda were a half, you're looking at all the numbers in this interval where at most half of the digits are equal to 9. Right? Now, what that means is as you look at bigger and bigger intervals, you have numbers with more and more 9s which are permitted, right? Because it's a fraction, it's like a positive proportion of the digits aren't 9. So that's a much, much larger set of integers that you are retaining in your set A. And their theorem, they have two theorems, or let's say two theorems. So you take a number, well, this is one theorem. I mean, they prove the if and only if part separately because one really uses some probability and the other is number theoretic and counting. So the series a to the lambda converges if and only if lambda is strictly less than 1/10. If lambda is greater than or equal to 1/10, the series diverges. So this is a nice, a very nice result, actually. That's interesting. What else? Oh, okay. So now I'm just going to mention a couple of results that are interesting. That's all I can say. I mean, so we're no longer looking at missing digits, but there is a semi-infinite literature in number theory that have to do with properties of the number S of n, which is the sum of the decimal digits of a number. Okay. And they're really interesting. I mean, Bourgain has a couple of papers on what the distributions of 0 and 1s are when you're in the binary representations of the prime numbers. So take a prime number, write it as zeros and ones, and you can actually say something about how many primes have binary representations with certain configurations of zeros and ones. So this is a stranger question in some sense. This is a question of Stan Ulam. So you let S of n be the sum of the decimal digits of n. And I don't know why he picked these numbers, but this was the problem he stated. Let n of x be the number of integers up to x, where n is congruent to 0 mod 13, and the sum of the digits is congruent to 0 mod 13. He asked, is it true that this set of integers has a density exactly equal to 1 over 13 squared? So of course, the number of integers congruent to 0 mod 13, that is 1 over 13. But he's saying 1 over 13th of them have their digits sum up to be divisible also by 13. Have anyone ever seen a question like that? So this question was answered also a long time ago, relatively long time ago, by Nathan Fine. And he proved the following more general result, which certainly answers Ulam's question. So instead of looking just at decimal representations, let's fix a number g, at least 2, and look at the usual g-adic representation. So, you know, writing numbers as sums of powers of g. Let S of n be the sum of the digits in the g-adic representation. Take your prime p. This should be a p over here. G not congruent to 1 mod p. Forget that. Let n of x be the number of integers up to x, which are congruent to a mod p, and where the sum of their digits, mod g, is congruent to b mod p. So this should be a p. So for any a and b, this is like 1 over p of the numbers, and of the numbers in this congruence class, exactly 1 over p of them satisfy this condition on the sum of their digits. That's what this says. The number of integers up to x is asymptotic, or the set has density 1 over p squared. So this is the first in a whole line of papers. I'm just going to mention one, which is due to, So this result was extended by Gelfond, not Gelfond, Gelfond, and others. And there's a paper of Gelfond, which has been cited probably 100 times at least, which generalizes Fine's result. Again, we're looking at g-adic representations, and S of n is the sum of the digits function. Again, this should be a p.
Yeah.
Yeah.
Obvious misprint.
Yeah, exactly. So whatever it is, doesn't matter. I can give you the reference to Gelfond's paper. So let's look at the number of integers up to x, which are congruent to a mod m, and whose sum of digits is congruent to b mod p. Then that set has density 1 over m times p. So this is 1 over m of the numbers, of all the numbers, and 1 over p of them satisfies this sum of the digits condition. Okay. I mean, for reasons I don't exactly understand, there really is a large literature on the sum of the digits function, to which, among other things, a lot of my friends have contributed. I have to confess, I never read any of their papers, but on this subject. But
can you extend it for asking for the sum of the digits to be mod not prime, some not prime number? Or are there
so I mentioned these things going back to Irwin. So everything I mentioned starting with Irwin's theorem has only been proved essentially for decimal representations. And all of these things can and should be extended. You know, I mean, they're all as far open problems as far as I know, but
Okay.
Hey, Mel, do you have any feeling for what's wrong with the prime being congruent to 1?
no. And I don't know whether it's an artifact of the proof or something essential. But but the fact that I don't know means nothing, because everything that I've spoken about, including my own theorems, are only, a few weeks old, really. So, so what I've done is done. It's written down. It is on archive. You can tell it's slightly weird because, if you write a paper on archive and, like you made some typos, you can correct it. So it becomes version 2. Or, if you improve something otherwise, you can correct it and it becomes version 3. And my paper is up to version 5 or 6 by now, because I thought I had proven something, and I had. But then it turned out you could do better. And then you could do better. And then you can do better. And at some point you stop, just because you get tired and, or in this case, because I had to give this talk. So I wanted to make sure that the preprint was on archive in case anyone wanted to look at it. But, and what I cannot remember is what chain of stream of consciousness led me, wherever it was, on MathSciNet or whatever, from one paper to another paper to another paper, until I got to that original paper of Kempner from 1914. But I did, and fortunately, the American Mathematical Monthly doesn't let you, unless you're a dues-paying member, you can't see the current issues. But an issue that's 100 years old is available on JSTOR or wherever. So, you go to MathSciNet, you click on article, and or maybe it is, I have to, it's on JSTOR, but your university has to pay to be a member of JSTOR, maybe. Because if I just do it directly on JSTOR, it asks for something or other. But if I do it through the CUNY library system, it goes right there. And I had read this paper of Kempner, which I thought was lovely. And then it's a natural question to ask about the sort of the general system of representing numbers to the script geodetic system. And what was interesting about that was that you can restrict digits, but still, but lose convergence. So the question, when you have these more general representations, when the harmonic series converge and when they diverge, that's when it became interesting for me. I mean, if I had only proven the analog of Kempner's theorem, that even in this larger class of number systems, restricting digits always leads to a convergent harmonic series, that would have been a nice, but not very, but less exciting. The fact that there's some properties of this system that give you a divergent series, even though you've restricted many, many digits, that I found a little bit unusual. Yeah, and there are other things left to say about it. I just, this is the state of the art as of the 17th of September. And we owe it all to COVID, right? Because I get to sit at home and spend hours at my computer going around through math. I mean, if I were on the train, if I had just taken the train to the Graduate Center, or if I had been driving back and forth to Lehman on Mondays and Wednesdays, losing 4 or 5 hours a day in my car, no way to do this. But God bless the Chinese.
The train was sometimes useful.
Right?
It was claimed that topology owes a lot to Penn Central Railroad.
Yes.
Topology owes a lot to the Pennsylvania Railroad, because Steenrod used to go back and forth to New York, and he would prove things on the train.
Yeah. Actually, you and I both get to do a lot. Would do a lot on the train. Train is good. It's the driving that I can do without. And I read somewhere about how Americans are saving time because of COVID, because the average American would spend 4 hours a week commuting back and forth to work. And I would spend 4 hours a day driving in and out of Manhattan or in and out of New York City. I mean, you spend an hour just waiting at the GW bridge to get through the tolls. So, you know.
Don't worry, with self-driving cars, you'll be able to do a lot of work.
That's true. If I could get in my car and just say, take me to Lehman. So I could sit in the back seat with my coffee and that would be great. Sure. I have a friend in Manhattan who was complaining about how his son is getting spoiled because his son has a friend whose parents are so rich that they not only have a house in the Hamptons, but they commute by helicopter. And my friend's 15 or 16-year-old son, when his friend invites him, they just go to the heliport, and all that traffic on the Long Island Expressway, they can just wave at it. Boom, they're there. So, and you can imagine a helicopter could land very nicely on the Lehman campus. There's plenty of room in the center there to where they have the baseball and soccer field. You can put a helicopter down there, but so actually it's probably harder to concentrate. Anyway.
It's always good to have goals, Mel. Always good to have a goal, right? Go for the helicopter.
Well, my goal
Mel,
is to figure out how, even when Lehman reopens, to teach synchronously on the internet. And it used to be at Lehman, there was always a big fight between the former president and the math department. The former president thought he would make his name by creating online courses. And he would force departments to offer some of their courses online. And in the math department, we would say, no, we're not going to do it. You know, we just refuse to do it because we think it's a bad way to teach. You want the students in the classroom with the teacher. And that's true. And I was as adamant, more adamant actually than most people against it. And it's true. It is it's infinitely better for students to be in the classroom with the teacher. But it is also true that I love working from home. So.
Yeah, I think it's better, but I think it doesn't have to be better. It's more like we don't know how to do it. How to like do online teaching properly. Like we haven't figured that out.
Well, if you're doing it synchronously, so it's live, and if students will log on to your posted office hours, you might say that maybe there's a small difference. There's a difference, but maybe it's less. But
well, so there was one class I taught for my brother, and it's much better than the classes I normally give in person. Part of it might have been that I was forced to prepare more because I was terrified of doing a horrible job. So, but what I ended up doing was we opened up this thing called CoCalc where we programmed together online.
Mm-hmm.
I was teaching them linear algebra by having them try to use this sort of like MATLAB type thing, Sage with me. And it worked really well. We were just typing on a file together.
Well, I'm curious. Does anyone except people at Lehman require a calculus computer lab to go along with the calculus course?
We do at Staten Island.
And does the department specify the program that's going to be used in the course?
No.
So it's up to the instructor.
Yeah, almost everybody has done MATLAB almost the entire time I've been there, but now there are several of us who are using Julia.
Uh-huh. And what about things that I've heard of, but I don't know what they are, like Geogebra?
As far as I know, nobody has ever tried to use it. Certainly the full-time faculty would be allowed to experiment. I don't know how much freedom we would give to an adjunct.
Do you know what Geogebra is? I
Yeah.
don't. Oh, what is it?
It's kind of a web interfacey version of, let's say, MATLAB.
Can you?
So you can draw circles and draw lines in, and the equations will come in. And
right, but I mean, can you? I don't know. If you give it 7 vectors, can you have it determine if they're linearly independent, or find the eigenvalues of a matrix?
So I haven't done anything with GeoGebra, but my impression is that it's Turing complete.
It's what?
That it's Turing complete. So you ask, can you do it? The answer is yes, but I don't know how hard it is, really.
But for example, in Maple and Mathematica, they're like packages that, you know, like if you want to solve a differential equation in Maple, you just write dsolve, and that's it. It's done.
Mm-hmm.
You don't have to program anything.
Yeah, I don't know GeoGebra well enough to answer those questions.
Mm-hmm. No, I mean, I'm always surprised because when we started our math lab at Lehman, it was a Maple lab. That was the syllabus. That's how it was approved. And then I was told some people started to use other programs for various reasons, one of which was some people just couldn't learn how to use Maple. And they use other things that were easier. And what I find is that when I teach, like I'm teaching a PDE course right now. So I'm having my students use Maple in that a little bit. And I do that in linear algebra, and I do that when I teach algebra. I mean, just because in Maple, it's just there are a huge number of things. And yeah, I don't know. Anyway, but you and I, our schools are the only ones that have a computer lab, I guess.
Yeah. The few, the proud.
I thought City College did too. Maybe Carlos can.
Yeah. No, Carlos was at Baruch.
Baruch. Okay. So I was substituting at City College at one point, and the students ran off to what they called Math Lab. So I assume it exists.
Yeah. Okay. All right. Next week, Harold Helfgott from Göttingen is going to speak. And I sent out, I think this morning. What?
He'll speak from Göttingen?
He will speak from Göttingen. Well, actually, I don't know where he's speaking from. He will not be speaking from the Graduate Center. I know that for sure. And actually, so he and I and a bunch of people were supposed to be in Lumini, Marseille last week. And I wrote to a friend of mine, Brudern, who is also at Göttingen. And I said, oh, you're so lucky you can go to Lumini and, you know, eat bouillabaisse, and I'm stuck in New Jersey. And he wrote back and said, in Germany, he's not allowed to go to the south of France. It's a high COVID area at the moment. And if he were to go, he would be forced into quarantine for a long time. And I was sort of surprised about that. So wherever Helfgott is, he's probably in Göttingen and probably not in Marseille. By the way, unrelated to the mathematics, but related to Marseille, on Netflix, there are various great series. And there is a series called Marseille. It's in French, but it's with subtitles, or maybe you can get it dubbed into English. But it really is good. It's about politics in Marseille. It's, who's the great French actor who usually plays this tough guy? At least
that of them, Alain Delon.
Alain, oh, I was gonna say that too.
But there is another one.
Yeah, it's the other one.
Who play the in Pierrot Le Fou? It's Monsieur Belmondo.
No, not Jean. No, Belmondo. Now I think Belmondo is dead. I assume he is. I don't know.
No, they're both alive.
No, so this is another guy, and he's gained 50 or 60 pounds since he played Tough Guys 20 or 30 years ago. But he plays the guy who's been mayor of Marseille for 20 years. And it's about the politics in Marseille between the center-right parties and the left and the far-right parties. But it's really, really, really good.
It's very good, but by the way, there is a great movie about early days in Marseille where both Belmondo and Alain Delon play. And I forgot how it is called. It's actually an American-produced movie, but if they very rarely play in the same movie. They play mobsters who just got out of jail in the 20s in Marseille. And it's really, they also show the political world, and they show the prefect of Marseille, who said that we don't get involved with gang violence unless they shoot our personal friends. Otherwise, they're free to do.
Yeah. Anyway, and I also discovered, so we watched that through 2 seasons, and it's Marseille French. For me, it's incredibly difficult to understand. And I used to think Parisian French was hard to understand. But when that finished, my wife and I started to watch another French TV series called Call the Agent, which is great, but it's pleasant. No one gets shot. It's lovely. And that's set in Paris. And that French, after watching 2 seasons of Marseille, is so much easier to understand. So
there is another great series, very, very humoristic, not very French humoristic, but French. It's called Most Secret Service. Mm-hmm. Or in France, Most Secret Service. It shows from inside how very realistically French Secret Service worked, at least for some time. Look at it, you will really laugh. And French
Tell me
is
again
very
what the title is.
What?
Tell me again the title.
I think Most Secret Service, or in France Secret Service, one of those. But I think it's not Netflix. I think it is, Amazon thing. It's an Amazon.
If you want something where you need the subtitles, try Professor T.
Oh, there are subtitles. There are subtitles.
But you need the subtitles. It's in Flemish.
That's very useful.
Not one of my best languages. Hey. Okay, everybody. Time to go. Next week, same time, same place.
Yeah.
Harold Helfgott.
Yeah.
Harold Helfgott, by the way, first spoke in our seminar when he was still a graduate student.
Mm-hmm.
He was a graduate student at Princeton, but he was doing his thesis with Ivanyets at Rutgers.
Yeah. If you are still up for seminars, an hour from now, Zollberger's seminar is on at Rutgers.
Is it listed on researchseminars.com?
I don't know, but you can probably find all the information at the Rutgers site.
Okay, good.
Or
Thank
a
you.
DIMAC site.
Oh, do you know what he's talking about?
Multiplying 3x3 matrices.
Oh, okay.
I've forgotten the speaker, but it's last week it was Neil Sloan.
Mm-hmm. Okay, bye everybody. Have a good week. Oh, Shana Tova to all. To whom it's relevant. Happy New Year.